Now let's jump in and talk about Riemann sums. So far, we have used rectangles to approximate the area under a curve, and the heights of the rectangles are determined by evaluating the function at either the right endpoint or the left endpoint of those rectangles. And there's other ways to do it as well. There's a trapezoid method, there's a midpoint method. So there's no reason to restrict it to just left-hand points and right-hand points, but those are the two big ones that we covered in this lesson. So now, when we use our summation notation to add up the area of each of those rectangles, we get that the area is going to be approximately I is equal to 1 to n of f of xi times delta x. So the xi's are the endpoints, either right or left, for the rectangle. So that, when you plug it into the function, this whole thing here will give you the height of the rectangle. This gives you the width of the rectangle. And you do that for each rectangle, and we stop at n rectangles. You can see here that n is that upper limit where we stop adding them up. This is what's called a Riemann sum. When you use the summation notation to add up your rectangles to approximate the area under the curve. Now, using the animation that I just showed you, we could see that as the number of rectangles got bigger and bigger and bigger, the width of the rectangles got smaller and smaller and smaller, and it gave us a better and better approximation. So we can say that the area under the curve is equal to the limit as n goes to infinity of the Riemann sums. The Riemann sums give better and better approximations the bigger that we get for n. So if we take the limit as n goes to infinity of that sum, we're going to get the actual area under the curve. In this next example, we're going to find the lower sum for f of x is equal to 10 minus x squared on the interval from 1 to 2. And we're going to use 4 rectangles. So our picture is going to look like this. 10 minus x squared is an upside down parabola that has a y-intercept at 10. So it's going to look something like this. And on the interval between 1 and 2, we need to make 4 subintervals. So first, let's figure out what the length of those subintervals are. So from 2 to 1, that's a length of 1, and then I'm going to divide by 4 to find the width. That's going to give me 0.25. So that's going to be the width of my rectangles. So this is 1.25, 1.5, 1.75. Now, the question is specifically asking for a lower sum, which means we want the rectangles to fall under the curve and not go over the curve. So we want to make sure that we're doing an underestimation. If I am going to do that with this curve, I need to do a right endpoint rectangle. I'm going to try to draw it nicely. So here are my rectangles. So it falls under the curve and not over. I'm going to highlight the endpoints that I need to use to find the heights of my rectangles here, 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 and here. So now if we want to create a Riemann sum for this, we're going to say we're going to write the sum from I equals 1 to 4, because we're doing 4 rectangles, 10 minus xi squared, and we have to multiply that by the width of each rectangle, which is 0.25. So to write this out, I'm going to take 10 minus, and my first endpoint is 1.25. I'm going to plug that into the function and square it. So this is going to give me the first height of the first rectangle, and I'm going to multiply it by 0.25, which is the width of the rectangle. And then I'm going to add that, and then I'm going to go to I equals 2, and I'm going to repeat. So I'm going to do 10 minus, my second endpoint is going to be 1.5. And I'm going to multiply that by 0.25, my width. So this gives me the height and the width of my second rectangle. Then I'm going to add that to 10 minus, and then I got to plug in my third endpoint, which is 1.75, and square it, and times it by 0.25. This gives me the area of my third rectangle. I'm going to repeat this one more time and do it for the fourth rectangle. I'm going to take 10 minus 2 squared, multiply it by the width of that rectangle. Now, when I put all of this in the calculator and I add it all up, I'm going to get 7.28. So the area under this curve is approximately 7.28, and because we made it so that it goes under the curve, this is going to be an underestimate. Let's look at this last example. We're going to find a lower sum for the sine x over the interval from 0 to pi over 2, and this time we're going to do 6 rectangles. So our sine function looks like this. At pi over 2 is where it peaks. So we're looking at this area under the curve from here to here. This is the area that we're trying to estimate from 0 to pi over 2. Now, we're trying to find a lower sum, so we're trying to do a lower estimate, which means we want our rectangles to fall below the curve. Let's figure out the width of our subintervals. So I want to take pi over 2, subtract 0, and divide by 6, and this will give me my width of my rectangle. So when I create my endpoints, I'm going to increase by pi over 12. So this first mark is going to be at pi over 12. Then the next mark is going to be 2 pi over 12, which is pi over 6. Then I have 3 pi over 12, which is pi over 4. Then 4 pi over 12, which is pi over 3. Then 5 pi over 12. And then 6 pi over 12, which is pi over 2. So we've created our intervals. And so now, when I create my rectangles, because I want to make sure that I'm doing a lower sum, I want my rectangles to be below the curve and do an underestimation, I'm going to have to do a left-hand endpoint. Here are my rectangles. And so let me highlight. These are going to be the endpoints that I use to find the height of my rectangle. So I'm using this one, this one, this one, this one, and this one. Now the first rectangle, because it goes down to 0, the height's going to be 0. But this, because this is a left-hand point, we're going to use that as an endpoint, but the area of the rectangle is going to be 0. So this is going to be my x1, my x2, my x3, x4, x5, and x6. So now to create our Riemann sum, we're going to start at 1 and go up to 6, and we're going to write the height of the function is going to be given by the value of the function. So we're going to write sine of xi times the width of the rectangle, which is going to be pi over 12. And we're going to do this 6 times. So we're going to get that the area is going to be approximately, when I plug it in for 1, my x1 is going to be 0. So I have the sine of 0 times pi over 12 plus the sine of pi over 12 times pi over 12 plus the sine of pi over 6 times pi over 12 plus the sine of pi over 4 times pi over 12 plus the sine of pi over 3 times pi over 12 plus the last one is going to be the sine of 5 pi over 12 times pi over 12. Now, when you put all that in your calculator, be very careful. It's a big mass. You also need to make sure that you're in radians. Since we're not using degrees, we're using radians. So plug that all in carefully. And when you do, you should get 0.863. So this is our approximate area under the curve between 0 and pi over 2. And because we're using the lower limit and our rectangles come below the curve, this is going to be an underestimate.